Hello everyone, and welcome to my another talk today. And today I'm going to talk about my favorite topic. And this topic is embedded domain-specific languages. Well, actually, I could talk about a more broad topic, just domain-specific languages, embedded or maybe external, but mm, I'm more interested in talking about uh, tips and tricks and mechanisms I use to build my eDSLs because this tool is super interesting. It's a very cool idea that helps to beat complexity quite a lot. We as software engineers, software developers, software architects deal with complexity of software all the time, and sometimes we cannot properly manage it because it comes from two places, and the first place is the domain. uh, the domain can be very difficult, super difficult, and mind blowing. So if you have a difficult domain, then certainly you cannot remove this complexity, but at least you can try to manage it to mitigate the problem by introducing domain specific languages that address the domain in its essence. So this can be a very viable solution if the domain is really big, rich, and complex. Another source of complexity comes from our decisions. This complexity is known as accidental, or maybe you might heard it as incidental. And this is where we introduce complexity ourselves. It's not natural to the domain. It's not natural to some business things, right? It comes with our decisions, tools, and approaches, and our duty as software engineers to keep this specific complexity low, to manage the domain complexity, and to keep accidental complexity low. Do not complicate our applications and code without real mm, need. So we have to deal with that. And embedded domain specific languages are super convenient for that. They help us to beat complexity uh, quite a lot. So, what we can say about domain-specific languages? Well, there are external domain-specific languages. They are not natural to our host language. They are external. They have own syntax, own grammar, own semantics, and this is we can say it's a separate language, maybe even a Turing complete language. Not necessarily. It can be a simple format of, for example, enumeration like YAML. It's an eDSL for configurations, right? It can be something more complicated. For example, we can consider uh, external DSL, some script language, for example, Python or maybe Perl or maybe Clojure. From some point of view, this can be considered an external language if you program in C++ or maybe in Java or maybe in something else. There is Lua, which is a Turing complete domain specific language, especially used in game development for various scenarios in games. There is Lisp as an external domain specific language in specific soft, for example, in 3D modeling tool 3D Max. I'm not sure if it's currently there, but long ago, Lisp was a part of 3D Max Studio, and you could program your scene in Lisp instead of just modeling it. Yes, so this is a very big topic because to parse, to evaluate and translate this kind of languages, you need to know how to do that. You need to have specific skills in parsing, in maybe in language design, in language translation. Uh, you would need to know about Backus-Naur form, for example, parser combinators, maybe regexp, maybe parser generators. This is a huge world, and we don't really recognize how to say the real need sometimes in this kind of languages. Sometimes we don't really know we need it, but many applications you might think about use external DSLs for their purposes. As I mentioned, 3D Max Studio or 3D Studio Max, I think, and maybe some games uh, for domain modeling and for modding. For example, there is test test construction set, which is specific tool for the Elder Scrolls series, for those games, to program your game, to program the world and items in that world. It uses, I'm not sure what exactly language is that. It looks like Java more or less, and you can program in-game events in that language. So yes, it's very widespread, although not simple and not easy to do. And there are embedded languages which I love, and those can be divided into purely type level, and actually you can build a fully type level language that will be types, only types. For sure, you need to descend to the value level, to the mixed level actually, values plus types uh, at some moment, because you cannot stay on the types level for the whole application. You need to do something real, but you can do that, and we will see several examples of those languages today. But most of embedded DSLs are mixed level. They use usual tools from specific language, um, and you can program quite various designs of those eDSLs using only your host language. There will be no external language. There will be no some grammar, just your host language, and your eDSL will be limited by the syntax and semantics of your host language. But it's not a big limitation because several design approaches allow to build super rich embedded domain specific languages, so rich you could not even recognize it was your initial language, for example C++, or maybe Haskell, or maybe Java, whatever. So let's move to the exhibition. I would say I've prepared several examples. Uh, Long ago, maybe 15, maybe 20 years ago, I created a, a text analyzer application as when I was a student. This was my thesis diploma project. This is a program that helps authors to polish their texts. Initially, it was built for the Russian language, but can be modified for something. And this text analyzer had two specific features. The first one is authorship recognition with uh, neural networks, simple ones, not as complex as today. And another part was euphony analysis. You could feed your text to this program, and this program will give you a map of euphony, or a map of how your text sounds, more or less. So there can be bad places when it sounds not very good. There, in red here, there can be good places. This is a completely made up example because I don't think I can run my program. It's C++. It doesn't age well. But anyway, it was the first very moment when I found that when I found the approach of eDSLs, and I didn't even know I am doing eDSL, but I needed it to simplify rules for that application, for rules of euphony. And you can see one of those rules. Let's remove that. This is a C++ code, but I tried to make it convenient to define those rules, except the rules themselves are not simple. They look like some regexp or something like that. But anyway, they can have many steps. Those steps can have many actions, and those actions should follow in a sequence way. And you can see here, I define those steps, I define some actions. I don't really remember what those actions mean, and I feed them using some operators. This is the syntax of the DSL. So I overloaded those operators, and there was idea how to structure the eDSL in a linear way. So yes, and then I create a rule, and this rule will be then evaluated. It is an interpretable language with several interesting, I would say, methods in it. So this is how it looks, but not very impressive actually. It's valuable to me because it was the first time when I found this idea and learned it and loved doing eDSLs. It was the first, but not the least. So let's move to another exhibition, maybe more interesting. This one, sorry. This one is a interactive project. As many other projects I have, it's not finished, but anyway, this is a Zork-like interactive fiction game engine, and maybe you know, maybe you've played those games. It's about a game you type commands in text, and the game responds with text when it explains where you are as a character, what you have to do there, what are the options, and etc. Zork, the Great Inquisitor, is one of those games. And Interactive was an attempt to recreate such a game. And I was interested in defining the locations, actions, and descriptions and objects in several ways. So I experimented with various designs. This was actually a free monadic language, free monadic eDSL, and not only one eDSL. For example, in here you see the location called west of house. So this is a location with several options in it. First, it has some description. It will be explained what this location is about. And also it has several options a user can do. This is a description of those options. It will be evaluated and will await for the user input and then pattern match over what was typed. So if you send a command open mailbox, you will read some letter from that mailbox. This is the idea, and the whole location graph can be described with such simple and quite mnemonic descriptions. I can show you more. So this is West House description, and there is reading action, I believe. Maybe, yes, you can have some action read and read what, because the player can read many things. Maybe it has something in their inventory, and then you can proceed with another location. Those things, they are transitions in this graph. The graph is a transition graph with nodes representing some locations. This is how it looks like. And this is an interpretable scenario. I would say AG graph is an interpretable language, free monadic language actually. I wanted to make it look and feel nice, so I first experimented with my simple designs and then came to this design more or less mnemonic, because I wanted those combinators look like transitions from something to something. And well, I could do it in a usual way for sure. I could use, for example, case constructions instead of this kind of pattern matching, but it was fun to find this design. Let me open several more files to see. This language contains several bits to describe containers, objects, and as I remember, I had a problem of defining those bits separately. I had the problem to create an extensible system. Extensibility in Haskell is a topic that I find not very well. I find it suboptimal, I would say, because Haskell lacks OOP style extensibility, but this extensibility is the most needed in real world applications. Well, at least it was so at the moment of writing this code, and I could not find a good way to make the code extensible, yet not polluted with type level bits, and maybe free from those type level bits at all, and the tricks Haskellers used to love to use, because most of them are based on type classes and specific type level things like type families and etc. But this kind of extensibility is actually not what needed in such a program. This is another topic, and I can talk about Haskell extensibility next time. So I don't think I found a good solution to that. And at that moment, I didn't know about good extensibility properties of free monads. So today I could redesign this and could have a much better language. So what else to say about that? Scenarios. What scenarios? Well, there is a scenario in some internal language, and this scenario is sequential. I don't really remember what it shows us. It describes some location and invites the user to do something, to play. Yeah. I won't demonstrate all the nuances of this language, but let's take a look at how it's done. So there is an adventure algebra, we would say, ADT. It's built specifically for being free monadic language. So you can see all the needed things here, like continuations and the next field, and etc. There are various basic methods in this language, this tiny eDSL. Seems like we can work with inventory and do something with user input output, uh, interact with objects, right? Do something with state, all right? So there are many things here, and actually the same, the very language with free monad. I see, and then we see helper functions. All right, so it's a free monadic eDSL, and it shows you how rich syntax can be, because using this free monadic language you can invent syntax like this, or maybe like something else in Haskell. In C++ this would not work, I guess. Haskell is very convenient for doing embedded domain specific languages, just because it has a functional nature, and the syntax when you pass arguments without uh, without commas and without brackets. This is a very interesting feature that helps us to build very interesting embedded domain specific languages. Yeah. Well, it's based on another free monadic language, transition graph. And those transitions come from here. There are various symbols here, so they represent various transitions, more or less mnemonic. Well, let's move to another exhibition. Sandwich, simple free monadic language for my book, and it's simple because I wanted to demonstrate the free monadic approach in its simplest form to teach. So there is a sandwich recipe language. Sorry, sandwich recipe language is a sequence of actions to construct a sandwich. We can start a sandwich, we can add components to it, ingredients, and then we need to finish the sandwich and get a ready sandwich. This is again an interpretable description. It doesn't interact with the ingredients you have in your refrigerator. It doesn't know about those things. They come when we need to run that recipe. So when we run, we call make sandwich. We pass this recipe to the runner, and we pass the existing ingredients, and then the machine will evaluate this recipe like it's cooking out. It's an automatic cooking machine for us. Yeah, it's simple, and again there are various ingredients here: bread, baguette, toast, and etc. Components: salt, pepper, cheese, whatever. There is sandwich body, which is incomplete sandwich, and there is a sandwich, I mean full sandwich, and a simple language that has only three methods: start new sandwich, add component, and finish sandwich. It's designed with an idea that you need to call finish sandwich to get a completed sandwich. But when you call those two methods, start and add, you will only have an incomplete sandwich. So there is some dependency between methods. You certainly can return an incomplete sandwich body, but actually you need to finish it, and it will be converted from sandwich body to sandwich. This is how you can make dependencies between your methods. It's called data dependency, or maybe value dependency. Yeah. simple. Yeah, let's move further. Andromeda. Again, it's a eDSL for a book, and it's very complicated eDSL, I would say. I won't demonstrate everything about that, just several samples. I see. No samples. This only. Let's make it bigger. Like this. Initially, this language was invented for designing SCADA scenarios for spaceship control. Because you might know that for controlling spaceships, rockets, and other stuff, people write really complicated scripts and logic in really complicated languages like C. But sometimes you can program those things using external languages. Many SCADA solutions provide an environment with an external language, uh, maybe more or less complicated, and you can program. I don't know, atomic energy stations, nuclear stations with some script like this, and this one is intended for controlling spaceship, for example, for sending rotation commands to it. It's not a very rich language because I didn't have a chance to develop a really complicated SCADA solution, but still, it has several ways to define network device of that spaceship. Network device can have computers and terminal units, various sensors, various drivers, and etc. Many various devices. So this language helps to control those things without knowing much details. Yeah. Yeah, and it's also a free monadic language. It has additional features like it can return something. For example, you want to create engine, it returns engine control. This control is a uh, how to say control structure design pattern, as I presented previously. The engine will be a separate actor, and when you create it, meaning connect to it, you will get a structure that you can use to interact with that actor. And this is a control structure design that utilizes envar request response design pattern inside, or something else to communicate with those actors. But maybe we need to move to the next eDSL, and this one will be a type level eDSL. Again, for another book, for demonstration purposes, Cellular Automata. I love Cellular Automata very much. Well, Game of Life for sure, and other. There are dozens and dozens of them, more or less interesting. But it happens that Game of Life is the most interesting of them, which is magic, because when you have interesting, when you have a field, for example, 3 by 3, and you can switch on or off those cells, you will get a neighbor of 8 different cells, and there is not many possibilities here. Well, actually, there are really many possibilities on how to combine on and off cells and have different neighborhoods. And this results in various automatas with own properties. If I'm not mistaken, it's about 200 200,000 of different automatas, and even more than 200,000. And it happens that Game of Life, invented by John Conway, is just one of those hundreds and thousands automatas, and one of the most interesting automatas out there, which is strange that he managed to find it, but still. So let's talk about the eDSL. This eDSL allows us to define those automatas on the level of types. And we can have neighborhoods. We can define those neighbors in terms of alive, dead, and alive. And combine those two neighborhoods to get a rule. So in this particular case, we define for Game of Life 3 for dead and 2 and 3 for alive. Otherwise, I guess dead. All right, if I'm not mistaken. And then, yeah, we can see it here. If we had a dead cell, then it becomes alive. All right, it becomes alive when we have 3 neighbors, and it stays alive when we have 2 or 3 neighbors. All right, otherwise we should turn the cell to the dead status. And configuring those things on the type level, you can specify other rules. For example, replicator. Replicator is a rule 1, 3, 5, 7 for both from dead to alive and from alive to alive. Interesting. Yeah. It looks like it separates on 2 identical chunks that are mirrors of each other. Then those can be separated into another chunks, and again mirrors of each other, and does it many times. Not a very useful automata, and not Turing complete. Game of Life is Turing complete, but replicator isn't. But still an interesting one. What's more interesting about this eDSL is that it has a dictionary. It has some possibilities to declare a dictionary of states, because it's not about 2-state automatas. You can have many states, not just on off, but maybe 5 states with different ideas. You can declare them here, those states, and you can enumerate those states here, and then you pass the states into the rule. And if you mentioned an existing state here, or you didn't mention any state that should be there, for example, there is a dead state and it's not used in the transitions, the eDSL will say you didn't complete your rule. It has some type checking possibilities on the level of types. So it prohibits many invalid states. Well, actually, it prohibits all invalid states, and there are at least 2 mechanisms of making those eDSLs type safe, and to follow the make invalid states irrepresentable rule. I am talking about those ways of doing that in the book, and won't pay any attention right now because it's a very complicated topic. But anyway, the compiler will know exactly what is it correct or wrong. So this was the idea behind this automata language. Another type level language is for defining Turing machine rules. Again, Turing machine is a classic example of evolution model. Both of them Turing machine and cellular automata classic examples of those models and can be expressed in both of them. Like if you have a cellular automata, like a game of life, I mean, as Turing complete one, you can build a Turing machine in it, and people did. Those automatas are just crazy. Those worlds are big and very strange, but they work like real Turing machines. Maybe not very recognizable because it's not a code anymore. Well, in some sense, it's code, just in a code in form of cells. But yeah, it's possible, and you can also write it cellular automata using Turing machine. But in this case, we write and encode binary increment rule. It's not complete because it's long. It has at least 6 states in my implementation. I believe it could be done more compact, but I only managed to do that with 6 states. It depends on what you need to do at the end. For example, if you want to move the head of the Turing machine to the first symbol of your binary number, then you will need extra steps. If you don't need that and you can stop in the middle of your number, then there will be less states. Well, that's quite not a very convenient way to define business logic, right? Or maybe complicated logic. Turing machines are very simple in this term. Too simple, too simplistic, too primitive. It's possible in theory, but I don't think you will be happy to encode things with Turing machines. And also, a classic mathematically defined Turing machine doesn't really interact with the real world. It only can read tape and write numbers, symbols back on tape. And that's it. It doesn't have a possibility to stop and ask the user to input something. You define a rule, you define an initial state, meaning tape with some numbers on it, and then you run it and until it stops, or maybe it will never stop, and we cannot predict for a general case. Yeah, we can take a look at the binary increment rule. So it's a state machine, simple state machine that is Turing machine. It has state definition. It can match the current symbol against some other symbols, and if something is matched, then it can evaluate actions. For example, skip the symbol and move the head to right, and go to the second state, or match this symbol and do that, or if nothing is matched, it will fail. And the second state, again, matching, it's essentially a conditional operation. Depending on the current input, we can do that or this, right? And etc. Just moving the tape left or right, writing new symbols into that tape, and reading what is currently under the head, and finishing state. Maybe I can move to the implementation bits, I mean how I define that, but it will be not an easy exercise because it's a type level programming in Haskell. And for example, here there is a custom rule data type, which is actually an algebraic data type, as we can see it here, but I use several Haskell extensions, meaning data kinds, that promote this structure from the mixed level. This is, I call it mixed level because you can define rule as a value of this type, and those be values. This value, value constructors. But when promoted upper, it becomes fully typed construction. This will be not a value constructor, but rather a type constructor, or maybe a type. And this will be another type. And this will be not just type, but rather a kind. And using those, we can achieve this syntax. It's a binary increment is a type, not just value, it's a type. Everything here is a type. A rule is a type. This is a type level string. Again, it's a type, but some may argue that those are not types, but rather type level values, which I find unnecessary because they have kinds and they can be placed into the variables, type variables, so they take places, take the same place as other types can take. So why not calling them types? But this is type level string, this is type level integer, and those are type level lists, and etc. Everything is type here, and this construction should be interpreted from types to regular values and then evaluated. Doing this interpretation, the same is true for cellular automata typed language, type level. We can check various invariants in compile time. The more invariants are on the type level, the more the compiler can check. And in this particular case, everything can be verified because everything is type, and using Haskell possibilities, we can traverse those type constructions in compile time and convert them to other forms or match them against some validator algorithms on the level of types. Yeah. So this is a construction that will become a type level algebraic data type eventually. But this is not the only truth, because the same structure is used for value level and mixed level operations. And actually there is even more behind that. When I declare a type for, type level eDSL with those things, I use this data and this data type. When I declare mixed level things, I convert from type level representation to a mixed level representation using the same algebraic data type structure, the same custom rule. And there is LVL that denotes what level of design, what level of code is used. Either it's a type level or it's a value level. And this is the so-called granular type selector design pattern, and there are additional extra bits to make everything work. For example, this one selects a specific string type depending it's a type level or value level, because on the type level we need the type called symbol. It will be specific to the type level, and for value level we need to select string as a type, and the two cannot be mixed. So this is a granular type selector that alters the field depending on what level we give it. So the structure can have fields with different types. The field can have different types depending on the level. And even more, this eDSL is not simple in any way, because it's a type level programming, and there are many things regarding how to convert it to a valuable representation. There is a static materialization phase. there is a dynamic instantiation phase, and many things related to that. But in general, this is how we design type level eDSLs. And one more example of type level eDSLs, again for the book. This is a DSL for declaring auctions, and this time it's an English auction type level eDSL. I can specify lots and what to do with those lots, and what is the round of defining who will buy that lot, who is eligible for buying that lot. Also, what lot is on the stake right now. For example, it's a Dali artwork or some vase from China, and etc. Again, everything is type level, and what's interesting about this specific eDSL, it's built with another Haskell type level features. It's built differently from the previous two, and it's fully extensible. Those two are not extensible. I prefer to call them configurable, or maybe generic, or maybe something like that, because you do not extend this language. What is provided to you, that's it. Nothing else can be added to the language. But you can configure your domains if they fit into the meta domain described by the language, as like here, 200,000 different automata are available for you if you for two-step automata. But if you add more states, then even more automata are available. But nothing beyond that. You cannot have automata that are continuous, that are not discrete, for example. Only those kinds of automata can be defined here. This is a limitation of the language. It's not extensible in this way, but the auction is extensible. You can provide extra bits separately from your original language, and they will be properly processed by the engine. And also, yeah, again, it's a type level eDSL, but it has a different idea behind. It's not just a data type. It's not just algebraic data type. It's now an empty algebraic data type with no value constructors, and fields are not fields from IDT, but rather type parameters of that IDT. And yes, it uses data kinds for promotion, but more of that. So it's a different way to construct type level eDSLs. Yeah. And probably the last one, again, a type level eDSL for specifying worlds of roguelike game Zeppel Rock. This one was needed for me to declare kind of type level OOP. Well, not just kind of, it's a real type level OOP. You can have abstract objects in this roguelike game, and those abstract objects can be inherited by other objects. I can show you. For example, we have an abstract door. It's an abstract property with several fields declared on the type level, maybe some scripts attached to those properties, and you can have different specifications or maybe extensions of that abstract type. It's an OOP, and it's more close to prototype OOP, like in JavaScript, rather than to class OOP. And this specific door will inherit previous properties like values, mm, values, fields, and scripts, but also it can alter those things and can rework if the script, for example, if it's needed to. OOP will be more or less uh, non-existent after you compiled it. But the structure of this language allows you to add methods to unknown types and define structures of unknown types up front, and everything will work. So this type level eDSL is extensible in this term. You can extend it by providing methods on the fly. Not here, it's a type level representation, but when it's compiled, methods can be altered in dynamically in runtime. So this is how well, there are even more things behind this language, and I made a whole stream about that. You can watch it. So it's not an easy language because those OOP bits really need some very smart, I would say, and very complicated type level magic, but still, yeah, it was needed to be a proof of concept. And also it was fun to develop this game, and well, actually it's not finished for sure. It's far from being finished, but still it's very interesting in my opinion. Well, that's it. Again, the slide. I was a guest on the Podlotka podcast. It's in Russian, and I was talking about domain-specific languages. So if you are interested to know more, welcome. I go to the details very much, not like here, but still. And yeah, the books, my books are very heavily infested or maybe packed with various eDSLs because it's a very powerful tool. And for today, it's it. So thank you. Yeah, it seems I lost mm, all my watchers, all my guests today. Maybe because it wasn't too easy. I'm not sure. So yeah, well, whatever. So thank you. That's it for today. And I hope you was at least impressed at what you can do with embedded domain specific languages. Yeah, I'm a bit tired actually. Well, I think nobody is writing any comments, so I can just finish the stream. It will be the last stream, maybe, well, whatever, doesn't matter. I need to rest a little bit because my thoughts are mixed, and yeah. So yeah, bye. Чего вы все разбежались-то?